Well, good day, students. And as I promised, today's lesson in video will be about the central limit theorem. So I've written the definition here again. And it says for all samples of the same size n greater than 30, the sampling distribution of the sample mean, which we did an example of in class, in which you have done at least one problem in 6.3 on, can be approximated by a normal distribution with a mean mu and a standard deviation sigma over the square root of n. Now, this central limit theorem is universal. It applies everywhere in the universe. Everywhere. It's almost like somebody designed things to be understood with a universal statistical theorem. And right? It's almost like something was designed that way. And so it doesn't matter what the shape of the distribution or how big the size of the distribution or how big our samples are beyond 30, the central limit theorem applies. And it works all the time, all right? And so let's discuss that here in a second. So let's write down the key elements of the central limit theorem so we can see them. Okay, this is really the most important part. This is the part you have to understand. Here are the key elements of the central limit theorem. First of all, there are two givens, all right? The first given is that our population is going to have a mean mu and a standard deviation sigma, okay? Those exist. And then our random samples or a random sample will be of some size n. Okay, those are the two givens. Now, we're going to then look at taking a sampling distribution of sample means. So we're going to get all the sample sizes of one size n, and we're going to then take a mean of each of those samples, and that's going to then create a new set of sample means. And we are then that's going to be our new population. All right? So that's why we call it the population of sample means. Now, the central limit theorem tells us this will be a normal distribution if the sample size is bigger than 30. Okay? The sample sizes from the original population. If they're bigger than 30, then this will be a normal distribution. And that the mean of all those sample means will actually equal the population mean. Okay? And so here's a new notation. The mean of sample means, which is the mean of a sampling distribution of sample means, is equal to the mean of the population. Okay, that's how you know that notation and what it is and how to be able to read it. Okay. The standard deviation of this population of sample means is going to be equal to this. New notation. The standard deviation of the sampling distribution of sample means is equal to the population standard deviation divided by the square root of the sample size. This is also sometimes called the standard error, and you will hear me use that vocabulary on and off quite quickly. Okay? And now here's the big one. The z-scores for these means we're going to converge the x bars, the sampling distribution of x bars, to standard normal values, which are z-scores. And we do that by this formula here. Z equals x bar minus the mean divided by the standard error. Okay? And then this mean can be the mean of the sampling distribution because they're equal. And this standard deviation can be the standard deviation of the sampling distribution, this standard error. So you could change the notation, but you're okay. Now, a couple of things we need to take into account as we move forward. What if the original population is not normal? And or the n values are less than or equal to 30, then the sampling distribution of sample means cannot be approximated by a normal distribution. So you have to use other methods, and those other methods are often called non-parametric, and that's beyond the scope of our class. That would be like if we had 2 semesters of stats, we would look at those methods. And so we're not going to have time for that. So this is a condition you have to pay attention to. So when you're doing problems, there are really 2 things you have to pay attention to. The first one is you have to check the requirements. Is the original distribution normal, or is the sample size bigger than 30? If so, you can proceed to approximate the sampling distribution by a normal curve. Okay? So this is proceed or not proceed, requirement 1. Requirement 2. Requirement 2 is you have to decide if the problem is about individual values or is it about the mean of a sample. There are 2 choices there. Okay? If it's about individual values, then we do it by the methods of 6.1 and 6.2, and our z is equal to x minus the mean over the standard deviation. But if it's the mean of a sampling distribution that you're trying to find something out about, then you're going to use our new z-score that we just listed up above. Okay? So those are the criteria, and let me see if there's anything else. Otherwise, we'll proceed forward and do problems. Okay, so here we go with the problems. We're going to talk about assuming that the weights of male college students, right here, that they gain during their freshman year are normally distributed, okay, with a mean of 1.2 kilograms. So, number 1, just so you know, for condition 1, the condition 1 was I need a normal distribution or I need sample size bigger than 30. So, since they said this was normally distributed, I can use the methods. I can go ahead and then use the methods listed in number 2. Okay? Just so you know. So, I need to think about that before I do the problem every time. Okay? It's really important for statistics. Okay? Now, the next thing we know is that we know the mean of this population is 1.2 kilograms. And we know the standard deviation is 4.9 kilograms. Now, why would it be the standard deviation be bigger? Because maybe in reality, if you think of male students coming to college, they tend to lose a little bit of weight, but there's a big standard deviation because there are quite a few who might gain weight. Like football players might gain weight because they're lifting weights, different kinds of athletes. But then other other types of people, if I came out of high school and I was kind of a doughboy, I might tend to thin out and lose weight. Or just eating college dormitory food. I don't eat as much as I used to and I'd lose weight. So this makes sense to me, and it may be real or it might not be real, okay? But it's the data we have for college men, okay? So I have that. So now I go to 5A. So now I want to look at problem 5A. And problem 5A says this, okay? It says if one male college student is randomly selected, find the probability that he has no weight gain during his freshman year, okay? So essentially, this is a normal curve of data. My mean is at 1.2 kilograms, okay? But I want to find the probability that his weight gain, he has no weight gain. So he actually loses weight or he gains 0 pounds. So 0 pounds is on this side, right? This is the data, x equals 0. And I want to find the probability that he has no weight gain. So here's the normal curve that represents that. Now notice, this is one male college student. So it's not a sampling distribution of means. I'm not looking at the mean of a sample. I'm just looking at what happens to this student. So this is basically a 6.2 problem, okay? All I have to do is find the z-score of this particular data, which will be 0 minus 1.2 divided by the standard deviation, 4.9. And that is going to equal, and so that z-score is negative 0.2448. And but if I use a table, I don't go beyond these two values anyway. And so those would be the two I'd use when using the table. Okay, so now I have my z-score. So that really means I have a new normal curve, right, where the mean is 0, and then I'm at negative 0.24, and I'm finding the area. It's the same area as the one before, so I can find that. And so I look on the table for 0.24, negative 0.24, excuse me. And the probability is 0.4052. And so then I would say the probability that x is less than 0 is equal to the probability that z is less than negative 0.24, which is equal to 0.40. Sorry, I lost it. 4052. All right. And so there's about a 40% chance that a student would be picked at random who had no weight gain. Okay. Now, just to remind you, let's do this again. I kind of jam-crammed this here. The original problem is that the student had no weight gain. That was this. We change it to its corresponding z-score, which is this. Okay? And then we look up the probability, 0.4052. And that's why this is the work I show along with my z conversion and my drawn normal curves. That's why that's the work I show. That's problem 5A. Now, just so you know, I can do this on a calculator. And so on the calculator, this would be a normal CDF. And we are going from negative infinity up to 0. All right. And so I'll do second distribution, normal CDF. Negative infinity, I use just a small enough number, negative 99,000. And then I'm going to 0. And then my original mean was 1.2. Whoops, I typed the wrong number. 1.2. And then the original standard deviation was 4.9. Okay? And then I can press enter. And so I put normal CDF and I put negative 99,000. I put 0. And then 1.2 was the mean. And the standard deviation was 4.9. And I press calculate and I get 0.4032. And so you can see the table gives us an approximation. The calculator will give us a much more exact value. And that's because we were really, we're missing this part of the z-score when we use the table. Okay? So that's the first problem. It's really a 6162 problem. Okay, so what I've done is I've just written a summary of problem 5A here. And so now let's go to problem 5B. Okay, and let's see what's different. So problem 5B says, if 25 male college students are randomly selected, find the probability that their mean weight gain during their freshman year is less than or equal to 0 kilograms. So the difference is, notice we're selecting a sample, whereas here we selected one male. And then we want to find the probability that their mean weight is less than or equal to 0 kilograms, whereas before we just wanted to find out if that one student was less than or equal to 0 kilograms, okay? So the difference is now we're doing this calculation based on a sampling distribution. So some information that I get here is n is equal to 25. That's the sample size. Since it was a normal population to begin with, it's okay that our sample size is smaller than 30. We can still use these methods. We want to find the probability that the mean weight, that the average weight of these 25 guys, or their average weight gain was less than 0 kilograms. So we need to turn that into a z value, okay? So that we can use our tables to calculate it. So how do we do that? Well, we use the transformation. So z is equal to the mean, which is 0, minus the mean of the sampling distribution, which is the same as the mean of the population, 1.2, divided by now the standard deviation of the sampling distribution, which is actually the standard error. So it's 4.9 divided by the square root of 25. Okay? So this then is going to be our z value in this case. And notice how the z value is going to be much different than what we got before. All right? So we take z equals, this will be negative 1.2 over 4.9 divided by 5, which is equal to, so you can see I got a different value here than what I got before. All right, the z from before, if you'll remember, was z equals 0 minus 1.2 divided by 4.9. And now we use the standard error because we're dealing with a sampling distribution. All right. And so that's negative 1.22. A note on calculator usage. This is negative 1.22 divided by parentheses 4.9 divided by 5. Whenever you have an operation within the fraction, surround that operation by parentheses so you end up not making mistakes. Don't just enter things straight in a row because you could end up making mistakes. And so this is a way to avoid that kind of issue. All right. So once we've done this, all right, we have our z value, which is negative 1.22. So now we can put that on the probability chart here. And that basically means we're looking at the table for negative 1.22 on the standard normal. All right, and so it's just a less than that probability. So I can look this up directly. And when I look that up in the table, really quickly, I'm doing that, negative 1.22, I get 0.1112. 0.1112. So there's only a 11% chance that the mean, that the average of the 25 guys will be that they lost weight. Whereas before, the chance of getting one guy who lost weight was 40%. So, and you can see the difference here. We're looking at comparing means, okay? And so now we go to 5C, and it says, why can a normal distribution be used in part B even though the sample size is not 30? Because the original population was normal, all right? Which means that the sampling distributions will be normal. So that's part of the choice. So there's your example right there, first example. Now, if you look at the rest of the problems, and so let's do that really quickly. So I'm going to expand this and we'll look at the rest of the problems. 6A, if one male college student is randomly selected, find the probability he gains at least 2 kilograms, okay? If 16 male college students are selected, find the probability that their mean weight gain during their freshman year is at least 2 kilograms. So, as you can see, this is a 6.1, 6.2 problem, whereas B, this is our 6.4 sampling distribution problem. And then they ask kind of the same question here, and you can do it because the population is normal, you're good. Then they go to 7A and B, and really it's the same questions as we've done before. They're just doing different probabilities. For instance, in the 6 problems, the probabilities are going to be greater than a value, so we have to use the 1 minus. In 7, the probabilities are going to be between 2 values, so we do the 1 minus the other because we're finding areas. So we're doing the problems exactly the same way as we did here, except we're using the standard error. And then number 8 is between as well. So I'll do 7 or 8 as an example, and we'll go from there, all right? Okay, so let's do another problem here. Oh, by the way, I should probably do this one by calculator. So normal CDF to check my answer. So I'm less than negative 1.22, so it's negative infinity. So this is our negative 99,000, negative 1.22. The mean is still 1.2, and the standard deviation is the standard error. Now, I can calculate this, or I can just let the calculator do it. And so let me get this out of the way here. Sorry, I'll get that out of the way so I can write it clearly. Wrote it too close. And so I can just put 4.9 divided by square root of 25 in for my standard error. This will calculate it, and I'll do that right now. And so there's the answer with the calculator. Now, it's slightly different than what we had before. So let's look at that really quickly. This was equal to 0.0067, and this is 0.1112. What's the difference? I think, I've rounded this off. So this is actually further to the left. It's like negative 1.227 or something like that. So it's actually less probability when you go from negative 1.22 and you move it over even just slightly, just a little bit, you move it over this way, you lose probability. And especially when you get here, like at this steep portion of the curve, you can lose quite a bit, 4 or 5% sometimes, with just a little move over. Okay? So in general, this is correct. Okay? Let's do another problem now. Just before I do another problem, the point is you can lose information, okay, with this, with round-off errors and so forth. So be cognizant of that as you move forward, okay? And just be aware of that. And this is why I want you to show this work, okay? Because this work tells me you understand the mathematics, okay? And for this class, I want you to understand the mathematics, and then I know that you'll be able to get correct answers. If you get an answer and all you show me are the answers, and if I don't know where they come from, then I don't understand if you know what to do. That's kind of the key there. Okay, let's do the next problem. I'll start it over here on the side. We're going to do number 7, all right? And so one male student, and he gains between 0 and 3 kilograms. That's the one we're doing, okay? And so we want to find the probability of gaining between 0 and 3 kilograms. Okay, so let's for one student, and then we want to do that for a sample of size 9. So then we want to find the probability on 7b for a sample n equals 9. Okay, so there's our 2 original probability statements. Let's go ahead and work on those now. And so I need to change this to a z situation, the probability that z is less than or equal. So I need to change both the 0 and the 3 to z-scores, okay? So for the A problem, that would be 0 minus 1.2 divided by 4.9, and I'll call that z1. And then that's going to equal negative 1.2 divided by 4.9. And that's going to be equal to negative 0.24. And then I want to do the 3, so I'll call that z2. And that's going to be 0 minus 1.2 divided by, did I put 1 point? Yeah, not 0, 3, excuse me. 3 minus 1.2 divided by 4.9, which is 1.8 divided by 4.9. And so 1.8 divided by 4.9 is equal to 0.36. So our z-scores are between negative 0.24 and 0.36. So I've now changed my original probability statement to a z-score. And now, if you remember how to do numbers in between, if we look at the area of the problem, we're going from from 0, the mean is 1.2, to 3 pounds. And so we're finding the area in between those. And so what you do is you take the area less than the 3 pounds and you subtract the area less than the 0 kilograms, and that will give you the area in between. So this is equal to the probability that z is less than 0.36 minus the probability that z is less than negative 0.24. That's how we did the ones in between. Now, if you change these to z-scores, you get exactly the same table, but the z-scores are now 0.24 and 0.36, which correspond to the x values of 0 and 3. So we've done the transformation. So there's our picture. Here's our conversion to z-scores. Here's our probability statement. And now we can look those up in the table. So I look up 0.36. And it should be 0.6406. And subtract the negative 0.24, which is 0.4052. And when we subtract those, we get 4, 5, 3, and 2.2354. So there's a 23% chance that we'll pick a random student that gained between 0 and 3 kilograms, okay? And that's how you would do that problem. So the next problem is essentially the same kind of problem, but now it's a sample of 9, okay? So let me do this, n equals 9, and here's our probability statement. 0 is less than or equal to x bar, because we want to see if the sample mean of those 9 students is going to be between 0 and 3, okay? And so we're going to rewrite that as the probability of a z value is between those. So we need to do the conversions. And so the conversion here, so z1 will be 0 minus 1.2 over the standard error, which is 4.9 divided by the square root of 9. Okay? And then z2 will be 3 minus 1.2 divided by 4.9 divided by the square root of 9 over the standard error. And so since it's a sample mean, now we convert it to the z's, and now we need to calculate those. So it'll be a negative 1.2 divided by 4.9 divided by square root of 9, which is 3. And so this one is a negative 0.73. And then this one is a 1.10. Okay, and so our z values are negative 0.73 to 1.10 now. And so now we can look up those probabilities on the table. Again, we're going to solve this in the same way. We're going to take the probability that z is less than 1.10 minus the probability that z is less than negative 0.73. Why do we do that? We do that because if we look at the picture, here's our mean, 1.2. The weights we're looking at are 0 and 3. This is our x data, okay? And so it's in between those, all right? And so if we take the probability less than 3 minus the probability less than 0, we take that big area minus the little area, and it gives us the area in between. And so if we do that, when we convert to z, we're going to do the same thing, except now it's negative 0.73. The mean is now 0 because it's standard normal and 1.10, and it gives us exactly the same picture. Okay, so I just need to find the probabilities associated with those z-scores. So 1.10, that probability is 0.8643. And I'm going to subtract the negative 0.73 probability, which is 0.2327. And that will equal, let's see, 0.6316. And so that's the probability. Now, each of these problems can be done using a calculator as well, so we want to at least do that to check. So normal CDF, the first problem is we're going to go from 0 to 3. The mean is 1.2, and the standard deviation is 4.9. Okay? And on the second one, we're going to do norm CDF, and we're going to go from 0 to 3. The mean is 1.2, but we're going to put the standard error 4.9 divided by the square root of 9, or just divided by 3. All right, and we'll just let the calculator calculate it, which is fine. Okay, so I'm going to punch those in the calculator and I'll show you. Okay, I've now punched those in the calculator, and you can see for 7A, the probabilities are close, 0.2354 or 0.24. All right. Actually, yeah, it's 0.2401. And then on the norm CDF with the sampling distribution, the answer is 0.6335, and the table value is 0.6316. So as you can see, you're close, but you're not exact. Okay? Same issue that we've encountered before. I think the problem I did earlier, I might have grabbed the wrong table value. These are enough different that I may have grabbed the wrong table value. So as you go through this video, you might want to look and see if I looked at the wrong row, which is typical. That's a typical mistake if you're that far off. These are close enough that I feel comfortable I did them right. This one was a little far off and caused me issues. In any case, there's problem 7A and B for you. And now you know how to show the work for the problem. Always draw the picture so you understand how to subtract the areas. Understand how to write the probability statements in terms of the original random variable, then in terms of the z-scores, and then how to find the probabilities based on whether you have to add areas or subtract areas, etc. And then check it with the calculator every time. Checking with the calculator is going to let you know if you do it correctly. And then just remember this trick, that for the standard error, you don't have to figure out what 4.9 divided by 3 is. Just let the calculator do it, and that'll avoid even more round off error. Okay? So it gets you a much more accurate answer. But this is how you do sampling distribution problems. Okay? Now, just for a quick review, if you remember, we reviewed the conditions of the problem first. Is it a normal set of data, or is the sample size bigger than 30? Okay? And then in problems 5 and in problem 7, each of those situations, the sample sizes were too small, but it was from a normal population, so you can use this technique to solve them. Okay? So there you go, 3 different problems. There's the original, there's the next one where I've made some mistake somewhere. Probably I looked up the value wrong on the table here for negative 1.22. Let me check that. Yeah, it's the same. So maybe I entered it wrong in the calculator. I could have typed the wrong thing in. And I have it written correct, but I may have typed the wrong thing. So in any case, that's how you do these problems. So good luck. We will see you tomorrow. And if you have questions, be ready to ask them in class. Okay? There's a little more on this section where we can talk about an introduction to hypothesis testing. That's sort of beyond the basics. And then there's also something about what do you do if you end up sampling without replacement and there's a correction factor. And so we can talk about those in class. So we'll talk to you later. Bye.